the advocate will refrain from making her opponent disappear.
This program is brought to you by Stanford University. Please visit us at stanford.edu.
All right, so let me just tell you what the story is with dark energy, big rips, whether dark energy will have a tendency to tear atoms apart and so forth. We're not. In past classes, we've studied a little bit about dark energy. So, for those who were there, I'll just remind you. For practical purposes, let's forget the deep story, but for practical purposes, dark energy, or cosmological constant, or whatever you like to call it, vacuum energy, the observed accelerated expansion of the universe, that is equivalent to a small repulsive force, a component to gravity. They say gravity is not repulsive. Well, suspend judgment about that until we get to it in this class. And imagine a small repulsive component to gravity, which is not proportional to 1 over r squared, like Newtonian gravity, but in fact where the force increases with distance. It increases with distance roughly the same way. Well, how about a spring? Supposing you have a particle on a spring connected to the wall, or 2 particles connected by springs. How does the force depend on the separation between them? The force grows linearly with the separation between them. Of course, until you break the spring, but let's not break the spring. The force grows linearly, and it's proportional to the distance between the particles at the end of the spring. Force grows linearly. There's some constant there, usually called the spring constant. Let's put it in. And because it's attractive, pulling the 2 things together, there's a minus sign there. Imagine that we have such a spring. Okay, now what, with 2 particles attached to it. What does the cosmological constant do? What the cosmological constant, the repulsive cosmological constant, what it does, a positive cosmological constant, or a positive dark energy, what it does is it adds a little bit of force of just this type, proportional to distance, but repulsive, not attractive. This is attractive. That's the minus sign there. Repulsive. So it adds a little bit of repulsive force to the otherwise attractive force between the 2 particles on the end of the spring. Now, I'm not really thinking about 2 particles on the end of the spring, but it's a good model for us. What I'm really thinking of, for example, is an atom. An atom is a system which is composed of 2 or more particles held together by forces. The forces are not entirely different than spring forces. But what would happen if you added to this a little bit of much smaller than the spring constant? The spring constant, which holds atoms together, is quite strong. The dark energy forces are minute. They're incredibly small until you get very, very far away. Notice this force grows with distance. Forget this one. We're going to add now a little bit of component. The coefficient in front of it is called the cosmological constant, or the dark energy, also times r. What would it do to the spring if there was a tiny, tiny coefficient here, and that coefficient is truly small for ordinary laboratory experiments? All it would do would be to change the equilibrium position of the particles at the ends of the spring a little bit. It would effectively change the spring constant here, make it a little bit smaller, But what would happen if you made the spring constant a little bit weaker? All that would happen is that the spring with the particles on it would be a little bit bigger. That's all. Atoms would grow by an entirely negligible amount. They wouldn't be torn apart. They wouldn't be torn apart. It would just change the equilibrium position of the electrons in the atom by a tiny, completely insignificant amount. And that would be the net effect on atoms. It would be the net effect on almost anything that was otherwise bound together. The reason is that this lambda here, how small is it? It's so small that this force doesn't become significant until you get out to the full measure of the entire global universe. That's where it begins to get big. But if you ask about it on the scale of the solar system, it's negligible. It's tiny by comparison with the other forces in the solar system, gravity and other things. And so what it would do is it would change the equilibrium position of the Earth a little bit, a tiny, tiny bit. Or it would change the size of a galaxy a little bit and expand it out a little bit. But it wouldn't overcome the forces which hold things together. Now, there's a theory called the Big Rip. It violates every principle of physics. It does. It violates every principle of physics. Why anybody would take it seriously, I don't know. But when serious theorists work out the equations and say there are limits between this and that, such and such cannot be bigger than this, or such and such cannot be smaller than that, for deep fundamental principles, somebody is going to come along and say, yeah, but what if those principles are wrong and such can be a little bit bigger or a little bit smaller than the bound that the theoretical principles tell you? Somebody will come along and say that. They'll write a paper about it. The paper will last till it gets to the New York Times, and then it will slowly fall into the junk heap of bad physics ideas. The Big Rip is one of those ideas. But I'll tell you, I'm not going to try to tell you right now what is wrong with it. We'll eventually come to it. But it's basically the idea that this constant lambda here is time dependent, that it grows with time. Now, there's no reason on Earth to believe that. Not only is there no reason on Earth to believe it, there are very, very strong reasons on Earth to disbelieve it. But you could say, who cares what theorists say? Let's make a prediction of what would happen if lambda grew with time. Well, if it grew with time, eventually it would become stronger than the forces which bind together other objects. At first, it would become stronger than the forces which hold galaxies together, and galaxies would fly apart. Then it would become stronger than the forces which hold the solar system apart. The solar system would fly apart. Then eventually it would become stronger than the forces which hold the spring together. Spring flies apart. As I said, that's called the Big Rip, that this constant lambda, the dark energy, is not a constant at all, but that it increases with time. Decreases with time is allowable. Increases with time violates some strong,
As I interpret what you're saying, lambda is a function of mass or whatever.
No, lambda is just a numerical constant, period.
Well, the point I'm getting at is, what if there's no mass? Is that lambda still in effect?
It's a force that would be there between any pair of particles if the particles were there. If the particles weren't there, there wouldn't be any particles to have a force on them. So it's
lambda evolves with time or changes?
No, according to most current thinking, it's called a cosmological constant for good reasons, because all of the good theory says it ought to be a constant. Now, could it not be a constant? It doesn't violate any very, very deep principles for it to decrease with time. It violates big principles to increase with time. So, but we'll come to this. I just wanted to assure you, to make you feel better about the future.
Things that dark energy is like a huge component when you start looking at stuff like gravitational thing. It's like 20-some%. So if it's so small, how can it have such a huge effect? You know, like why?
Well, the dark energy density in this room is tiny. It's extremely small. I'll tell you how small it is. Take a cubic meter. And how many protons worth? A proton has a certain mass, E equals mc squared. So there's a certain amount of energy in every proton. Roughly speaking, I think the dark energy in this room per cubic meter would be, I would have to work it out, but it's roughly of order about 1,000 protons. 1,000 protons in a cubic meter is a negligible amount of energy. Its gravitational effects on things are really negligible. But if you had it smeared out through the entire universe that way, then at sufficiently big distances away, now imagine now we live in a world which has an extra bit of energy that's causing repulsion, but it's spread out throughout the entire universe in a smooth distribution, then eventually at sufficiently large distances, it would make an effect, a repulsive effect on things which would become big. But those distances are cosmological in size. So it has an effect on the global universe, but it doesn't have an effect on, certainly not on laboratory physics. It doesn't even have a significant effect on any kind of astronomical physics. By astronomical, I mean things smaller than the entire universe. In fact, for whatever reason, this number happens to be such that this force only becomes significant and comparable to other forces at something like the radius of the entire universe. So it only becomes important under those circumstances. People who want to tap the vacuum energy, to get vacuum energy to do work, and as a solution to the energy crisis, have to deal with the fact that if they wanted to get a tank full of gasoline, they would have to extract the energy out of a volume something like the orbit of the moon or something like that. So there's not a lot of energy there. Yeah. And no way to tap it, but...
Would that suggest that dark energy is really a relative energy?
Relative to what? What does it mean? I'm not sure what you mean by a relative energy. Do you mean, well, it gravitates. It gravitates. It has the effect of a distribution of mass in the universe. So it's, you mean are only differences of it important? Is that what you meant? I'm not sure what how relative was being used.
I'd have to, try to elaborate on that probably.
Yeah, it's probably.
I heard that someone said there's no particle associated with dark energy. Like, they aren't really.
No, not with dark energy. Dark energy does not have the form of any energy that's associated with particles. We'll come to it. I hope we'll come to it in the course of these lectures. But no, there's no particles. Now, dark energy is to be contrasted with what's called dark matter. Dark matter is an entirely different thing, a totally different thing, and it really is made up out of particles, or at least it's believed to really be made up out of particles. But this is not where I was going tonight. I just wanted to, for those who were involved in these exchanges of email, I thought I would give you my view of it. Let's come back to the Newtonian laws of gravity. We need to spend a little more time with Newton before we can move on to Einstein. And when I say Newton, of course, many of the things I'm going to say, Newton might not have really recognized, but they are forms of, or expressions of Newtonian physics. First, a little bit of mathematics, and it's not really mathematics, it's just formalism, ways of expressing equations, symbols. All right, first of all, I told you last time we used the symbol del last time. It's called del, upside down, delta. And it's thought of as a kind of vector, but it's not really a vector with definite magnitude and definite directions. It stands, just like every vector, if I wrote any vector over here, v, we could say that's the same thing as giving its components, the x component, the y component, and the z component. So one way of viewing a vector is just that it stands for three numbers. The x, y, and z components of v could be a velocity, for example. Okay. The symbol del with an arrow above it stands also for three objects, but those three objects are really derivatives. Derivative with respect to x, derivative with respect to y, and derivative with respect to z. So whenever you see a del, it always means you're differentiating something. You're always doing a derivative of some kind, a partial derivative or a set of partial derivatives of something. Now, for example, how do you use it? It's really called a differential operator. It's not a set of numbers, it's a set of operations. But it also has three components. So let's say, the first example. The operation del, if it acts on a scalar. Now, a scalar just means a function of position, function of x, y, and z. I'll stop writing x, y, and z soon enough and just call it x. But take a function of x, y, and z and apply to it the operation del. What does it make? It makes a vector. Phi is not a vector, but del times phi is a vector. And what are the components of the vector? The components of the vector are just derivative of phi with respect to x, derivative of phi with respect to y, and derivative of phi with respect to z. So it creates a vector from a scalar. That's one example of the use of del. Another example, supposing it acts on a vector field. It can also act on a vector field. What does it mean? Let's take del dot A. Let A be a, let's use V. Del dot V. That's called the divergence of V. We talked about it last time, but just to give you a little more feel for how the symbols are used. Dot stands for dot product. If I have two vectors, let's call one W. For a moment, let's call one of them W, and let's call the other one V. And I take the dot product of the two vectors. What it stands for the x component of W times the x component of V, plus the y component of W times the y component of V, plus the third term, which is similar. That's the meaning of W dot V, the standard old-fashioned dot product between vectors, which most of you have seen. All right, by the same rule, we simply pretend that the symbol del stands for a vector. It's like W, but it's not a real vector. It's just a set of operations. And what this gives is the derivative of Vx with respect to x plus the derivative of Vy with respect to y plus the derivative of Vz with respect to z. In other words, it has the same form except replace W by this set of derivative operators. Right, so it's a neat notation. It's a notational device for doing certain kinds of derivatives, partial derivatives, on various kinds of things. Now, if phi is a scalar, then del dot phi is a vector. What if V is a vector? What is del dot V? It's a scalar. In the same way that the dot product between two vectors is a scalar, the divergence of a vector is a vector. These notations are pervasive throughout all of physics, electricity, magnetism, gravity, and without them, we would not be able to, we wouldn't be able to function very well. Okay, that's just a preliminary warm-up and definition. It's really just definition. There's not any deep mathematics. The deep mathematics is, of course, in the notion of a derivative or a partial derivative, derivative along a direction. Now, I mentioned, of course, that phi here is a function of position. A function of position like that is called a scalar field. It's a scalar, and it depends on position. Depending on position like that makes it a field. V, the components of V may also be functions of position, and in that case, V is called a vector field. All right, so anything which depends on position is called a field, and that's our basic notation. All right, let's come to the field, to the gravitational field. The gravitational field is a property at every point of space, and let me define it for you. First of all, let's imagine that it's created by some masses. So let's imagine some masses, some mass points, and I'll label them as usual I, J, K, where I, J, and K run from 1 to whatever. And let's call this over here the ith mass. Now, what we do to define the gravitational field is we invent another mass. We imagine one more mass, which we'll call the test mass. The test mass is a little tiny mass that we move around in space, and we examine the forces on it. And in terms of the forces on it in different places in space, we define a field. And that field is a force field, or strictly speaking, a field of acceleration. So here's what we do. We take our little test mass, and we hold it and we let it go. And we see how much acceleration it accelerates with and in what direction. Acceleration is a vector. It has a direction. It has a magnitude. And that acceleration, the acceleration experienced, let's draw a little test mass. The test mass I'll just draw with a little cross in it there. All right? It may or may not be real. It may just be in our imagination, or it may be a very small little mass that we move around and explore the vicinity of the real masses. And that acceleration is a vector. It depends on position, and I'm not going to write x, y, and z now. I'll just write x, x now standing for x, y, and z. That acceleration, and let me write it down for you. Let's call the vector from the ith mass to the test mass, the vector pointing from the ith mass to the test mass, let's call that r sub I. Last time I had defined the vector as the vector from the test mass to I. Now I'm defining it to go from I to the test mass. Those two vectors are equal and opposite to each other, but by defining the vector r sub I as the vector from I to the test mass, I will save myself a minus sign. Which direction? Sorry. I think I want it to go the other way. If I want to save myself the minus sign, I want to make it go the other way. Yeah. Ri goes that way, from the test mass to the particle which is creating the gravitational field. Now, which way is the force on this object due to the ith mass? It's pointing toward the ith mass, right? The gravitational force on the test mass is pulling toward the ith mass, and so it's along the vector r sub I, not opposite to it, and that will save me having to write a negative sign. All right, so now, what do we know about this field of acceleration? Well, it gets a contribution from every real mass here. And the contribution in particular from the ith mass, it's a sum. A is a sum over all the masses a sum of all the real masses. It depends on the gravitational coupling constant, on Newton's constant. It depends on the distance from the test mass to r. That's r sub I from r sub I squared. And what else? And it depends on the mass of the ith particle. Each particle has a mass. The acceleration on this particle due to the ith particle is proportional to the mass. It's proportional to g, and it's divided by r sub I squared. But everything that's written here, none of the things that are written here are vectors. G is a number, m is a number, and r is the length of a vector. Its square is just a number. There's no vectors on the right-hand side, so there's got to be something wrong with this equation. What's wrong is I have to remind myself what direction the acceleration is. And it's along the direction r sub I. So the way to deal with that is to put another r vector here, but then we have too many r's in the numerator. We have to put another one in the denominator. We have to make this cubed. Because the length of this is r. Another way to think about it is to leave it as r squared and think of this as a unit vector. The symbol for a unit vector, a vector of unit length, is a vector with a little hat on top of it. Little hat on top of it means unit vector, a vector of unit length. All right, so this vector here is a vector. It tells you the direction of things. It tells you the direction of the acceleration, but the magnitude of it all comes from here, and we add them all up. The acceleration on the test mass is a sum of vectors, all different contributions. This depends on position. For example, the further away we take it from the distribution of mass over here, the smaller it is. If we bring our test mass right up to one of the particles here, there's a great big force on it. If we bring it on the other side, the direction switches. So this A here is a field. It depends on position. And it's called the gravitational field. All right, there's a way to summarize this, which is neat. We talked about it last time. I'm not telling you anything I didn't tell you about last time. But the way to summarize it is in terms of the divergence of A. Let's look at the del dot A. That's the divergence of A. And let's look at, let's just take a simple case. The simple case, let's suppose there's only one mass point. If there's one mass point here, then let's look at the gravitational field in the neighborhood of that mass point. Well, it's pointing inward. If I take my test mass and move it around in the vicinity of the heavy mass here, I'll discover a gravitational field which varies from point to point, always pointing toward that mass. Right? So the gravitational field, the vector field, points inward toward that point. The inward pointingness of it is called the divergence of the field. The divergence of the acceleration field here is due to masses, and it's proportional to the mass. At every point, there's a divergence which is proportional to the amount of mass at that point. To express it mathematically, we have to invent a concept called mass density. Now, we all know what we mean by mass density. It's not a new concept for most of you. Mass density simply means take a volume of space, ask how much mass. We're now imagining that either that the mass is continuously distributed, not in the form of point particles, or that there are so many point particles, tiny, tiny point particles, that we might as well effectively think of it as being distributed. Then the amount of mass in a unit volume, or the amount of mass per unit volume, is called rho, equals mass per volume. We take a small volume, count up all the mass in it. Delta M over delta V is called the mass density, the mass per unit volume. And of course, it varies in general from place to place. Here there's no mass per unit volume. Here there's mass per unit volume. So the mass per unit volume is itself a field. It's the density field. Right? On the left-hand side here, we have the divergence of A. The divergence of A is a vector field, but its divergence is a scalar. The relationship between masses and gravitational field, which is basically the relationship that Newton wrote down, here it is, can be re-expressed in the form that del dot A is equal to minus 4 pi, I'll tell you in a moment, I'll remind you where the 4 pi comes from, why it's there, times the mass density, times Newton's constant. The strength of gravity is always proportional to Newton's constant, so the effect of a mass is always proportional to Newton's constant. It's proportional to the amount of mass, that's the rho, and this is the basic equation that you can think of as a field equation. It relates two fields, the field of acceleration to the field of mass density, and the constant g is just a constant in the relationship. This is called Gauss's law. Why is there a minus sign here, incidentally? Well, the minus sign simply takes into account that if you have a mass point there, the acceleration field is pointing inward, so you don't really have a divergence, you have a convergence of the gravitational field, but a convergence is just a negative divergence. So that's why the negative sign is there. Right. This is called Gauss's law. But there's another thing which is named after Gauss, and it's Gauss's theorem. This is a law of nature. This is equivalent to Newton's relationship between the acceleration field and the mass densities. It's something that you get from experiment, or if not, well, from experiment or observation. But there's a mathematical theorem, which is Gauss's theorem, which also has to do with divergences of vectors. So let me remind you about Gauss's theorem. It is so central to everything and certainly in gravity theory, that I feel justified in spending another 15 minutes on it, another 10 minutes on it. Gauss's theorem says that if you have a field which has a divergence, that divergence is a scalar, and you take some region of space, any region of space that has a boundary. It could be a sphere, doesn't have to be a sphere, it could be a sphere with two ears sticking out of it. It should have the topology of a sphere. In other words, it shouldn't be a donut, but it should not have holes in it or anything like that. Even then it's okay, but let's just take it to be a chunk of space like that. Then what Gauss's law says is that if you integrate the divergence over the volume dx dy dz inside the region. And how do you do that? What does that mean? That means you break up the region into little cubes, three-dimensional cubes. You break it up into tiny three-dimensional cubes. In each cube, you take the divergence of A, you multiply it by the volume of the little cube, and you add them all up. Okay? That's integrating the divergence of A over the interior region here. What it says, or what Gauss's theorem says, is that that integral is equal to a surface integral, a sum over the surface. So let's draw the surface here. Let's draw a piece of the surface. And also now break up the surface, the bounding surface, also into little squares, little cells. All right? And in each cell, the field A has a component perpendicular to the cell. It may also have components in the directions parallel to the surface, but A has a direction perpendicular to the surface. Let's call that A perpendicular, or A sticking, the component of A sticking out of the surface. It says that Gauss's theorem says that the integral of the divergence of A over the interior is equal to the integral over the boundary. That's usually called d sigma. Sigma stands for little surface area, stands for little surface here. The integral d sigma of the component of A sticking out of the surface. In other words, it's just adding up all the components of A sticking out of the surface. I told you what the significance of this would be for the flow of water if the divergence of A stood for the divergence of the velocity field of water. Then it would just be the amount of water being pumped into a region here is equal to the amount going out through the boundary. But this is Gauss's theorem. Let's just isolate Gauss's theorem now. The integral over a volume of the divergence of A is equal to the integral over the surface of the component of A perpendicular. Now, that's Gauss's theorem. Now let's put them together. Let's put them together to see how they work together. Let's imagine first that we have a distribution of mass which is spherically symmetric. That means it doesn't have any dependence on angle in space, that the distribution of mass has the symmetry of a sphere, symmetry of rotational invariance. Another word, there's another word for having symmetry of a sphere. Anybody know what it is? It's isotropic. Isotropic means the same in every direction about a central point here. Okay? All right, so it could be a ball of material, but it doesn't have to be a solid ball of material, but it should be shaped like a sphere. Okay. So we have some mass in here, and I want to know what its gravitational field is. What I do is I surround it nice and spherically symmetrically, concentrically, with a sphere. I apologize for the fact that my drawings are two-dimensional. If I had some way to make them three-dimensional, I would, but I can't. So they're two-dimensional versions of surrounding a spherically symmetric distribution of material by a shell, by an imaginary mathematical shell. Can the red be seen? All right, so there's a red shell around here. Now let's see what this says. All right. First of all, we integrate up del dot A. But what is del dot A? From Gauss's law, not from Gauss's theorem, but from Gauss's law, we know that del dot A is 4 pi minus 4 pi times the mass density times g. So let's work that out. So we're going to get minus 4 pi. We're going to get g. And then we're going to get the integral of the mass density over the interior of the sphere. The minus 4 pi g can come on the outside of the integral since it's only a constant, and the integral itself just gives us this integral is just what you see here. Now what's the integral of rho over volume? That's the mass. Integrating up the mass density just gives you the mass enclosed. So the mass enclosed within the red sphere. Okay, so let's rewrite that. That's minus 4 pi g times the mass within the sphere. If the red sphere is bigger than, let's call this a planet. Let's call it the planet. If the red sphere is bigger than the planet, then it's the entire mass of the planet in there. Minus 4 pi mg, or minus 4 pi g. M is the left-hand side. What about the right-hand side of the equation? The right-hand side of the equation says, take the perpendicular component of the acceleration of the gravitational field. Now, if the mass distribution is isotropic, the gravitational field will also be isotropic. In other words, the component, the perpendicular component of the field will be the same everywhere. It'll be pointing out with the same component everywhere's on this sphere. So that means that the perpendicular component of A doesn't vary from point to point on the sphere, and that means that this integral here is just the perpendicular component, whatever it happens to be, times the integral of d sigma. What does the integral of d sigma mean? It's just the area of the sphere. It's just adding up all the little area cells of the sphere, and that's the area of the sphere, which is 4 pi r squared. R here not being the radius of a planet, but being the distance from the center of the planet to the red sphere. Okay, so now you see why the 4 pi was in Gauss's law, why Gauss put it into his law. It was in order to be able to cancel that out at this point. It was arbitrary. You could have defined things differently. Now, we solve this for the gravitational field, and what does it tell us? It tells us that the gravitational field of a mass is minus mg over r squared. Something we already knew, that's Newton's law, that the acceleration due to a massive object is the mass of the object times g divided by r squared. But it gives us a nice, we talked about this last time, I'm just going back over it. It also tells us that it doesn't depend on the mass having all been concentrated at a point. All it depended on was the mass was spherically symmetrically distributed. Okay, so I did this again to point out to you that del dot A equals minus 4 pi rho g is equivalent to A being the sum over all the mass points of Newton's characteristic expression for gravitational field. So that's cool, huh? It's a nice way to express things. This summarizes the very, very complicated equation on top of it. It doesn't look so complicated, but if you wrote it out for lots of mass points and so forth, it would become complicated, whereas here's a way to express it where it's rather simple. While we're at it, somebody asked me last time about the gravitational field within the Earth. What is it like within the Earth? Here we did the gravitational field outside the Earth. We can now carry out a calculation of what's going on inside the Earth if we like. It's kind of interesting. All we have to do now is take our red surface, same calculation, but now take the red surface inside the Earth. But now we have to be careful, because the amount of mass within the red circle, the red sphere, is not the total mass of the planet anymore. It's only the mass within the red sphere. So let's do the calculation over again. The right-hand side stays the same. The right-hand side is still 4 pi. In other words, the perpendicular component of the field times 4 pi times r squared, where this r is now the radius of the inner sphere here. What about the mass within the red sphere? How much mass is there within the red sphere? Well, for that we have to make some kind of assumption about how the mass is distributed throughout the red sphere. Let's make the assumption, which is not so bad for the Earth, it's not a bad approximation for the Earth, that the mass density within the Earth is uniform. The mass density is uniform inside the Earth, and then when you get to the surface of the Earth, it drops abruptly to 0. That's not exactly true. It's denser near the center than near the outside. But let's take that as a model. A uniform mass per unit volume within the Earth. Then how much mass is inside this red region here? It's not the total mass of the Earth now. It's different. So let's calculate it. It's the volume of the sphere times the mass density. Yeah, this is equal to minus the mass within the sphere, and the mass within the sphere is the volume of the sphere, 4/3 pi r cubed. That's the volume of the sphere times rho. Four-thirds pi r cubed times rho. I think I got it right. Oh, on this side. G, good, thank you. All right, we can cancel out some things. We can cancel out the 4 pi's. And now we can divide by r squared. If I divide by r squared, what I get is A perpendicular is equal to minus 1/3 rho times G, 1/3 rho times G, times r. What does this say? This says that the acceleration of a test mass, of course, we would have to drill a hole through the earth if we wanted to drop a particle. We can't drop particles if they're stuck in the rock. But if we had some sort of particle, well, either we drill a hole through the earth and drop particles down, or we drop particles which don't interact with the material of the earth. Neutrinos don't interact much with the material of the earth. We drop a particle, what does it do? Well, it experiences an acceleration which is toward the center. That's the minus sign here. The perpendicular component of A is negative. That means it's toward the center. It's got some constants in it, rho, g, and 3. Those are just numbers. But it grows linearly with the distance from the center of the Earth. So it's an acceleration, which means a force. If I were to multiply this acceleration by the mass of the test particle on both sides, then I would have the mass on the test particle. The mass on the test particle is toward the center, and it's proportional to the distance away from the center. There's a name for such a system. It's a harmonic oscillator. A force which is proportional to distance. In other words, a particle displaced from the center will be pulled back to the center exactly as if it were on a spring, with a spring constant that depends on the mass density, depends on the gravitational constant, and it depends on 3. So if we dropped a particle, if we drilled a hole through the Earth and dropped a particle, it would just oscillate up and down like a harmonic oscillator. I forget the time constant. I think it takes about 10 minutes for it to go through the Earth and come back, or something of that order of magnitude. This is not important to the general theory of relativity. It's just another example of how to use Gauss's law and Gauss's theorem to solve what would be a very hard problem if we had to add up the contribution of every particle in the Earth. I mean, just think about it. How hard that would be, yet this method allows us to do it easily. Okay. Any questions?
Is there some reason why the distribution of the matter outside of the shell is negligible?
It's not just negligible, it's 0. That's a good point. Okay. Right. So let's talk about this. Yeah. That's right. That was one of the consequences, and one of the curious consequences. I'm sure it gave Newton some pause when he realized it, but that's right. It is only the material inside the sphere which contributes to the gravitational field. The material on the outside all cancels out. The gravity from here and the gravity from here and the gravity from here, they all cancel out. Newton knew it, and he proved it without calculus, which is quite the reason he proved all these things without calculus is because none of his audience knew any calculus, and so he had to do everything geometrically. But we see it from Gauss's law. Gauss's law tells us, among other things, that the gravitational field of a spherically symmetric mass only depends on the mass within the radius r, and doesn't depend at all on the mass outside the radius of r. A consequence of this, I think we talked about it last time, but might as well just say it again, is that if the mass was entirely distributed on a shell, imagine the mass was on a shell, thin shell, then inside the thin shell there would be no gravitational field at all. Particles would move around as if there was no gravity at all. On the other hand, particles outside the shell would see the gravitational field of the shell exactly the same as if it were a point at the center. So that's a rather remarkable fact, and it's special to the 1 over r squared law. Notice that it tells you, assuming Gauss's law and Gauss's theorem, you get the 1 over r squared law.
I'm having a hard time equating those two figures at the surface of the Earth. I get a 4 that I can't get rid of.
Oh, did I miss? I may have missed a 4. Let's see, where? Where? Shall I go back? I need to go back a step here?
No, the expression there on your right, the lower there,
Yeah.
equating that to the expression on the board to your left, at the surface of the Earth.
Wait. Left, this and this?
Well, those two gravitational accelerations should be the same on the surface.
What should be the same as what?
A bar on the right board should be the same as A perpendicular on the left board at the surface of the Earth.
Oh, at the surface of the Earth. Good. Did I make a mistake? Did I lose a factor of 4 somewhere? I may have lost a factor. Is it a factor of 4 that's missing? 4 pi. From which one? Oh.
He's already canceled the 4 pi in that.
Remember what Feynman
You're absolutely right. They should agree at the surface of the Earth. So someplace I lost a 4 and a pi, but this one, of course, is correct. That's just Newton.
Well, the mass.
You canceled them because they were on both sides.
That row and the other one.
That was on both sides of the equation.
One person. Does somebody see where I made a
It's
mistake?
a row with the mass.
You canceled the 4 pi's because they're on both sides of the equation.
The row has to be function of the mass. One you have row, one you have mass. So you have to.
So let me go back. Let me go back and do it. Okay. All I hear is a buzz. Oh, okay. One has row and one has mass. Yeah. Oh. Okay. No, it was right. It was right. Yeah. That's right. That's right. No. All right. To those who didn't follow the last discussion, forget it. It was right. All right, one more concept which is important before we get on to relativity and the equivalence principle, or the equivalence principle in particular, is the idea of gravitational potential. Just one point. The gravitational field is a field of acceleration. Yeah.
Is the gravitational shell?
Yeah.
Is the gravitational field continuous? It seems like
No, it jumps at the shell. It jumps at the shell. As you go from outside the shell to inside the shell, it jumps.
Does it discontinue?
Right.
Derivative is discontinuous, right?
The field itself is discontinuous.
Well, if the shell has a finite thickness.
If the shell has a finite thickness, of course, then it's smooth. But if the shell was literally an infinitely thin shell, then it jumps. Right. The gravitational field jumps.
Now, the equation you had here said that the force or the acceleration varies linearly from the center of the Earth.
Yeah.
And yet,
until we get to the boundary of the Earth.
You also said that if we consider a series of shells, the force on an object is all the shells outside can be neglected and all the shells inside.
Right.
But the mass of a subsphere, whatever, is not linearly dependent on the.
No. That's right. We canceled out. Yeah. Okay. So let's go back. No, let's go back. We had on the left-hand side. We have on the left-hand side of the equation the gravitational field times the area, r squared. That was one side of the equation. The other side of the equation had the mass, which you correctly say was proportional to r cubed. Divide by r squared, and we get A proportional to r. That's what we did. The r squared, the area grows as r squared, the mass grows as r cubed, and therefore the gravitational field is like 1 over r.
Could you just derive that equation again?
Which one?
The one that you erased on the board behind you?
This one?
Yes, please.
Okay. It's Gauss's law again. We take a sphere which is smaller than the size of the Earth. Okay. One side of the Gauss's law gives us the total mass within that sphere. Is that clear? Who asked the question? Yeah, is that clear? All right, so one side of the equation is the mass within that sphere. What is that? That's 4/3 pi r cubed times the density. Well, we also have to throw in a g. A g? Yeah. 4/3 pi r cubed times rho is the mass within that sphere, and we multiply it by g. That's one side of the Gauss's equation here. The other side of the Gauss's equation is the integral of the component of A sticking out from the surface. That's equal to the surface area 4 pi r squared times A perpendicular. And there's a minus sign there. So we have on the left side something like r cubed. On the right-hand side, r squared. I can cancel the 4 pi and then divide by r. If I cancel the 4 pi, I get g over 3 r cubed rho is equal to minus r squared A perpendicular. And now divide by r squared. Dividing by r squared leaves 1 power of r there. So it tells me that the gravitational field is linear just like a spring. Okay?
Now, on the surface of the Earth, you can equate that to mg divided by r squared.
Yeah.
Okay, mg is 4/3, m is 4/3 pi r cubed.
So it's missing a 4 pi that you
It's
have
still-
on the right.
This one is missing a 4 pi?
The
No.
left, you're missing the 4 pi multiplying g.
No, it's not. It's canceled on both sides.
All I'm asking you to do is equate them and see if they're equal.
It's got to be the volume times the rho.
Think of rho as the whole Earth.
No, I'm looking at mass. The mass of the Earth is 4/3 pi r cubed.
4/3 pi r cubed times rho.
Right. Okay, so on one side you have 4/3 pi r cubed. You have a 4 pi, and on the other side you don't.
Is that good or bad?
That's bad.
Oh, okay. I thought I did it carefully, but maybe I made a mistake. Let's take a vote. How many think I'm right? All right. Let's do it during the break. During the break, I'll go through it with you. And it is not entirely possible that I make numerical errors.
It's how you get to m is by doing the integral.
Yes.
And that's where he misses the fourth.
Yeah. So when you go, we'll work it out in detail during the break. Okay, I was going to talk about gravitational potential, but I think I'll do that next week. And I want to get on to the equivalence principle, a little bit of some new physics. This, of course, was all old physics, and it's taken us another hour to go through Newtonian mechanics. Just a repetition of what we did last time, but let's move on now to the equivalence principle. Now, the equivalence principle, of course, is the principle that says that a field of acceleration is in a certain, that acceleration and gravity are the same thing. But to make it specific, the elevator analogy is a good analogy. Now, for reasons that are a little strange. I'm going to have my elevator accelerate horizontally. It's just because I want to use the coordinate and call it x instead of y. You'll see why. We'll get to it. All right, so we have an elevator. Somebody stands in the elevator. I want to emphasize that this has nothing to do with this room. It could be in any direction that the elevator is accelerating. It could be accelerating by means of a cable or whatever, rockets, I don't care, whatever, pulling it. And it's being pulled with an acceleration, let's call that acceleration little g. What about an object that's dropped by the passenger within the elevator? All right. That object, according to Newton's laws, in a frame of reference outside the elevator, in an inertial frame of reference, watching this, that object stands still. But what does it do relative to the person in the elevator? Well, the elevator person gets accelerated that way with an acceleration g, but he doesn't say he's accelerated. He just says, I'm standing still, and he sees the little thing that he dropped accelerate toward the floor, and of course accelerate toward the floor with exactly the acceleration g, but not toward the right. He sees it accelerate toward the left. So he says there's a field of acceleration inside the elevator. There's an A field inside the accelerator pointing downward. Everything he drops gets accelerated downward, exact downward meaning to the left, exactly as if there was a gravitational field, a field of acceleration pointing to the left. How big is it? Well, it's just exactly equal in magnitude to the acceleration that the elevator is moving with, little g, and so he says there's an acceleration field of strength g pointing toward the floor of the elevator. Okay, looks like gravity, sounds like gravity, smells like gravity. The conclusion that Einstein came to, and this, you might say to yourself, why did it take Einstein to say this? Almost any small child who's been in an elevator would have recognized it, that gravity, the effects of gravity on everything that this person does, juggles balls, does whatever he wants to do, is exactly identical to what he would experience if he were in an elevator being accelerated. Gravity and acceleration are the same thing, according to Einstein. Or in other words, the physical effects of being in an accelerated elevator are identical to the effects of gravity. Now, as I said, that seems almost trivial. I'll tell you what, let's take a break and then come back to some discussion of its non-triviality, why Einstein was called Einstein instead of Joe Palooka. All right, so let's talk a little bit about how Einstein used this idea of gravity being the same as acceleration. He didn't just say that, but he used it. And let's go through one application of it and then start to discuss some ideas about the general theory of relativity. So now let me return to before I do that, there was some reason why I put the elevator horizontal. It had to do with a graph that I want to draw. Let's talk a little mathematically about what it means to be in an accelerated frame of reference. The accelerated frame of reference was the frame of reference as seen by the passenger in the elevator. His or her frame of reference. Okay, so x is horizontal. That's why I had the elevator going horizontally, because I wanted to use x. And I want to plot x along the horizontal axis. And along the vertical axis, I'm going to plot time, t. This is all of space-time. X, well, I haven't plotted the other directions, y and z, but time and x, and that's the world inside, inside and outside. Now, let's first talk about what it means for a frame of reference to be uniform velocity. Before we get to acceleration, let's just suppose the elevator were moving with uniform velocity, not accelerated. Let's call the bottom of the accelerator floor, let's call that x prime equals 0. In other words, we have two frames of reference. Me standing on the outside, and I have a coordinate which I measure by meter sticks, and I might measure it from right over here, 1 meter, 2 meters, 3 meters, 4 meters, and so forth. All right, so that's my frame of reference, and I call my coordinate x, and here are the ends of the meter sticks. Meter sticks, end of the first meter stick, this is x equals 0, x equals 1, x equals 2, and so forth. All right, now what about an observer, somebody in the elevator, who's moving with uniform velocity? He has his coordinates. He stacks up his meter sticks in here. His meter sticks are not the same as my meter sticks. My meter sticks are standing still in my frame. His are moving in my frame. And he will call the bottom, the floor of the elevator, he will call that x prime equals 0. Prime means in the frame of reference of the passenger. Prime for passenger. Okay? So there's also an x prime coordinate. Let's take x prime equals 0. That's the floor of the elevator. The floor of the elevator is moving. And so the floor of the elevator looks like that. As time goes on, the floor of the elevator moves further and further to the right. Not only does the floor of the elevator, but x equals 1 follows along, and x equals 2 follow along. Those were intended to be parallel. I'm not sure they are. So the moving frame of reference measures distances relative to the floor of the elevator over here, whereas the stationary frame of reference measures distances relative to x equals 0 over here. Now, what's the relationship between x and x prime? Well, let's take any old point over here. This is a point in space and time. It's a point of space at some time. And let's ask what its x value is. Its x value is the distance to here. In other words, it's the coordinate that the stationary observer sees. Just call it x. What about x prime? X prime is the distance to the floor of the elevator. The elevator is moving, so x prime is this distance. What's the difference between them? The difference between them is just the distance that the elevator has moved. Velocity of the elevator times time. That's how far the elevator has moved in an amount of time t. It's moved with its velocity. It's moving with a uniform velocity, v times t. So what is x prime? Here's x prime over here. X prime is equal to x minus vt. That's the relationship between the primed coordinate and the unprimed coordinate. And this you better get used to, this idea of relating frames of reference like this. That's the relationship between the moving frame and the stationary frame. Now, there's one other thing in Newtonian physics. We're not yet doing relativity. In Newtonian physics, all observers measure the same time. Time is the same for everybody. And so we can write another equation that t prime is the same as t. This is Newtonian physics. This is not yet relativity. This is not yet Einstein. It gets modified in Einstein. But this is the relationship between the coordinates measured by the moving observer and the coordinates measured by the stationary observer. It's a coordinate transformation. X prime is x minus vt. T prime is equal to t. Now, let's suppose now that there was an object which is standing still in the outside frame of reference. This guy drops his ball here. The ball stands, let's say it stands still in my frame of reference, just for fun. How does it move in his frame of reference? If it's standing still in my frame of reference, what is it doing in his frame of reference? I'm in particular interested in the velocity. All right, so if a ball is standing still in my frame of reference, it means x is equal to a constant. It's just standing there still. The elevator is going by. The person in the elevator is looking at the ball, sees it moving. All right, if x is a constant, then x prime is, of course, just minus vt. But what I want to do is differentiate this equation with respect to time. What does it say? It says that x prime dot, I'm using dot to indicate time derivative. Standard notation, we've used it before. A dot indicates a derivative with respect to time. That's equal to x dot. But if x is constant, if it's standing still in my frame of reference, that's 0. What's the derivative of minus vt with respect to t? Just minus v. So this was a long-winded way to say that the velocity of the ball as seen from inside the elevator is minus v. Of course it is. The object was standing still in my frame of reference. The observer is moving past it with velocity v, and of course sees it moving backward relative to him with velocity minus v. That's all this says. Okay. What does it say about the acceleration as seen in the moving frame of reference? Let's differentiate it one more time. Differentiating it one more time, that gives us the acceleration in the prime frame of reference. What's the derivative of v with respect to t? If v is constant? 0. So if it's not accelerating in my frame of reference, it's not accelerating in his frame of reference. It's very simple, okay? Trivial, in fact. But now let's suppose that the elevator is not moving with uniform velocity, but that it's moving with uniform acceleration. Then the distance that the elevator moves is not vt. What is it? Supposing it's moving with uniform acceleration, a acceleration equals little g, the acceleration due to gravity. Then how does the floor of the elevator move relative to me if it's accelerating like that? Well, it doesn't move on a straight line, it moves on a curved line. It moves on a parabola. If it's uniformly accelerated relative to me, it's moving on a parabola, and that parabola is x equals 1/2 gt squared. Is this known to everybody? This is a standard formula for uniform acceleration. Yell out if you don't know it. Okay, this is the elementary calculation of a thing moving with uniform acceleration. So the moving observer's, the floor moves to the right 1/2 gt squared. Along with the floor, all the other meter sticks, the end of all the meter sticks do the same thing. They accelerate off on a curved path in space-time. An acceleration means a curved path in space-time. So let's see what the relation between x prime and x is. Again, same thing. Here's x prime. Here's x. What's the difference between them? The difference between them is x minus 1/2 gt squared. This distance is 1/2 gt squared. The distance from here to here. X prime is x minus gt squared. This is the new transformation for transforming to an accelerated frame of reference. Okay, let's say again that the passenger drops a coin, or whatever it is, and that the coin happens to be standing still. He throws it in just such a way that it's standing still in my frame of reference. That again means x is a constant. What does it say about x prime? It says that x prime, well, let's work it out. Let's work it out. What does it say about the velocity? If x is standing still and we differentiate this, we get the velocity in the prime frame of reference, 0 from differentiating x, standing still in my frame of reference. But what happens if we differentiate minus 1/2 gt squared? Minus gt. But I'm interested in the acceleration that the observer in here sees, so I differentiate it again. X prime double dot. The acceleration seen from inside here. What do I get when I differentiate it once more? Just minus g. This is a mathematical statement of the simple trivial observation that acceleration works the same way as gravity. The accelerated elevator gives rise to an acceleration for anything that you drop, which is just minus g, just like in an ordinary gravitational field of the Earth. So anything which is dropped in this accelerator, in this elevator, accelerates toward the floor, not in the direction of the elevator's acceleration, but in the backward direction. That's the minus sign here, and it accelerates backward with the acceleration minus g. Okay? So that's a mathematical statement, but what I wanted to bring out is that it really has to do with using a set of curved coordinates. It has to do, or that acceleration is really the choice of a curvilinear set of coordinates to describe space-time. That's the real lesson here. Acceleration, an accelerated reference frame is described by a coordinate transformation to a set of curved coordinates. Right, so we need to keep that in mind. The connection between gravity and curvature we're beginning to develop. But having done that, let's now come back to some simple physics. One of the things that Einstein became instantly famous for, we can work it out qualitatively, it's the bending of light. Okay, so his first step was to say, I really mean it when I say that the laws of physics in a gravitational field are the same as the laws of physics in an accelerated reference frame. And in particular, not just the laws of Newtonian mechanics, but the laws of everything. Nobody at that time had the faintest idea how gravity affects electric and magnetic fields. They didn't know. In fact, I don't even know that the question was asked at that time in a serious way. And so it wasn't known, for that reason, it wasn't known how gravity affects the motion of light rays. What Einstein said is, I now know how gravity should affect the motion of light rays. So here's his elevator. Now I'm drawing the elevator vertical. The elevator will accelerate upward. And let's suppose a light beam is shined from one side to the other. First, suppose the elevator is not accelerating. Let's suppose the elevator is standing still, and you shine a light beam. What does it do? It goes in a straight line, and it goes right across the elevator. It hits this point over here. Now what happens if the elevator is accelerated upward? Well, let's send the light beam, just arbitrarily, let's send the light beam at exactly the instant when the elevator begins to accelerate. It's not yet moving, it's just beginning to accelerate. So the light beam starts moving off horizontally. But now the the elevator is accelerating upward. And so where does the light beam hit the other side of the elevator? Down here somewheres. And it travels in a curved path. In fact, that curved path will be a parabola again. It'll travel on a parabolic orbit. And that parabolic orbit, you can work out easily just from the motion of the elevator. And what do you find? You find that the light ray has a downward component of acceleration which is equal to g, the same acceleration. If the elevator is accelerated upward, with acceleration g, then the light ray will have a downward component of acceleration, which will also be g. So by that little argument, nothing more than that, Einstein deduced the fact that light falls in a gravitational field. As I said, this was unknown. Nobody even suspected it, that the existence of heavy masses which create gravitational fields would cause light to do anything other than travel in a straight line. In fact, light doesn't travel in a straight line when it passes through the Earth, passes across the Earth. Why? Because the gravitational field of the Earth can be thought of as an upward acceleration. And so light will fall. Let's go through.
Question?
Yeah.
Suppose you shine the light in the direction of the acceleration.
Yeah. So it's a little more complicated. It still has an effect, and it affects the energy of the light ray.
But it won't affect the speed.
No.
Because that depends on...
Right. The acceleration in the vertical direction will correspond to change in energy of the, yeah, it won't affect the speed. That's correct.
One more question?
Yeah.
The Eddington experiment that verified general relativity.
Yeah.
If you take plain old Newtonian mechanics and assume that a photon is a particle of mass E over c squared, and just use Newton's gravity equation, will it properly?
Yeah, let's do it. Let's do it. Let's do it.
And that's what, in fact, that's general relativity predicts exactly the same thing.
By a factor of 2. But let's see if we can roughly work out the bending of light by the sun. Okay. The question is this: if a light ray passes the sun, and clearly Einstein has already proved that light falls in a gravitational field, so he wanted to estimate. The first thing he did before he had the full apparatus of the general theory of relativity, he had as much as I've explained up till now, and he said, I will try to estimate how much the light bends. In other words, what angle does the light ray get accelerated? What's the right word? Deflected. Yeah, by what angle does the light ray get deflected? All right, we can make an estimate. Now, at this point, he was reduced to estimates because he didn't know the details of how the spherical Earth, with its varying gravitational field, would really affect things. But in particular, he was interested in a light ray which just skimmed the surface of the sun. Got as close to the sun as... Why? Because the effect would be maximal the closer the light ray got to the sun. Of course, he wasn't interested in light rays that went through the sun. Light rays don't go through the sun. A light ray that just barely skimmed the sun, how much it got deflected. Okay, let's see if we can figure it out. First of all, in passing through the, when it passes close to the sun, it has an acceleration toward the sun, which is just the acceleration field of the sun. So when it's in the vicinity of the sun, let's break it up. When it's out beyond the distance comparable to the radius of the sun, it's too far from the sun to feel anything. When it's within some region comparable to twice the radius of the sun here, it feels the gravitational pull of the sun. Right? What's the acceleration that it feels downward? Well, for that, we just have to work out the acceleration due to gravity. What we have to work out is how much acceleration is there at the surface of the sun. I think we already had a formula for that, right? The acceleration due is m, mass of the sun, g over r squared. That's the, do I have that right? mg over r squared downward, right? Everything gets accelerated downward, light as well as everything, and all with the same acceleration. So mg divided by r squared is the acceleration, the vertical component of the acceleration, right? How much velocity does how much vertical component of the velocity, now vertical doesn't mean toward the sun, it means vertical on the blackboard here. How much vertical component of velocity does it have after it passes the sun? Well, to calculate the change in velocity, you multiply the acceleration by time. Acceleration times time is the change in velocity. So you take this acceleration and multiply it by the amount of time, let's call it delta t, that it takes for the light beam to cross across the radius of the sun. Now, we can estimate that because we know how fast light moves. It moves with the speed of light. So how long does it take? It takes a time, delta t, which is approximately twice the rate, this distance here, divided by the velocity. That's velocity times time equals distance. So time is distance that it travels divided by the velocity, but what velocity? The velocity of light. The velocity of light going across here. So that's 2r divided by c. So let's plug that in. That gives us another 2. The 2 is not important. R divided by c. And what is that? That's twice mg over rc, right? That's the downward component of velocity here. But that's not the angle. The angle is basically the ratio of if we have a small angle relative to the horizontal, here's the horizontal, small angle relative to the horizontal, that's the velocity, this is the direction of the velocity after it passes the sun, then the downward component here, the angle, is the ratio of the downward component to the horizontal component. The downward component divided by the horizontal component is essentially the angle, at least if the angle is small. So the angle, let's call it theta, is equal to the ratio of the downward component, here it is, 2mg over rc, that's the downward component of the velocity, divide that by the horizontal component of the velocity, and that gives you the angle. Another horizontal component of the velocity is 1 over c, and here's the answer, 2mg over rc squared. That's a very small angle typically, mainly because c is a big number and g is a small number. So g is a very small number, c is a very big number, c squared is even bigger, and so that's typically a small angle when the light ray goes across the sun. So that was the crude estimate that Einstein made. I can't remember what the correct answer is from the general theory of relativity. It's within a factor of 2 of this. I think maybe it's just exactly either twice this or half of it. I can't remember. And so every light beam that passes by the edge of the sun gets deflected by that much. Right? That was Einstein's prediction. It was verified by looking at stars passing across the sun during an eclipse. We don't need to go through that. Most of you know the story. But the main point here is that Einstein used the idea that gravity and acceleration are the same, something that was known to everybody, but he used it in a context which nobody had ever thought of. Namely, he applied it to the motion of light and to electromagnetic phenomena in general. Okay, so that's now, yes, gravity is like acceleration, but that idea is pretty much limited to a uniform gravitational field, a uniform vertical gravitational field. It doesn't really make sense when you try to think about it globally in terms of the Earth's gravitational field when you stop thinking of a flat Earth approximation. So here's the Earth. The effect of the Earth's gravity on anything over here, out here, Einstein said is exactly the same as if you were in an elevator over here accelerating upward with a certain acceleration. Well, first of all, the acceleration has to be different in different places, different direction in different places, different magnitude in different places. And so there's no overall sense in which you can take the gravitational field of the Earth and replace it by a single accelerated frame of reference. The acceleration has to be this way over here, this way over here, this way over here, this way over here. So there's certainly no sense in which the full gravitational field of the Earth can be replaced by saying you're in an accelerated reference frame. What you can say is for a small amount of time and over a small amount of distances which are too small to detect the fact that the gravitational field has different directions in different places. In other words, on a small elevator, for a small amount of time, the effect of the Earth's gravitational field is the same as the effect of an accelerated elevator, but only for a small amount of time. Why? Because, well, unless you allow the acceleration to change with time, but for a small amount of time, you can pretend that small amount of time and a small amount of space, not enough space to feel the change in the direction of gravity, you can say that gravity has the same effect as acceleration. But if you really think about it, I mean, you have to think much more deeply about what the gravitational field of the whole round Earth is. Now, this is related to something else. If you're freely falling near the surface of the Earth, you don't feel the effect of gravity. You can tell the difference between free fall and not free fall, but there's no difference between falling at the surface of the Earth and being out in the middle of space with no gravitating objects at all. What about somebody falling over here? Can somebody falling over here, just in free fall, can they or can they not tell the difference between falling and being in an elevator, so to speak, or being uniformly accelerated? What's the right word? Can a person over here tell that they're falling, as opposed to being in outer space? Can they tell the difference between gravity and acceleration? And the answer is yes. They can tell the difference because the gravitational field of the Earth is not uniform. It points in different directions, and it varies with distance. So that means an observer, here's an observer, a cubic observer. A cubic observer has a different gravitational field on them in different places. The bottom of his feet is being pulled harder than the top of his head, so he's being stretched that way. The gravitational field is sort of pinched in toward the center here, and there's some sense of being squeezed this way. You know what those are called? Those are tidal forces. We talked about tidal forces last time. Tidal forces are real. You can feel them, but in order to feel them, you have to be large enough to sense the variation in the gravitational field. So the right statement is, if you're small enough and for a small enough amount of time, then the gravitational field, you don't feel it in falling, and it can be completely replaced by being in an accelerated frame of reference. Gravity and acceleration are the same. But if you're big enough to feel the curvature of the Earth's surface, and if you're big enough and you wait long enough time, and you can feel the variation of the radial component of the gravitational field, then you can definitely tell the difference between being in outer space and being in free fall. Free fall isn't so free. You get squished one way, stretched another way. These are tidal forces. The effect of tidal forces are an obstruction to eliminating the gravitational field by replacing it by an accelerated frame of reference. All right? You can't really replace a gravitational field by an accelerated frame of reference except locally and over small times. So the equivalence principle is a limited idea that makes sense only in this limited sense. Okay? There's an obstruction to getting rid of the gravitational field and replacing it by free fall, by a field of acceleration, and that obstruction is tidal forces. There's no way that you can construct an accelerated frame of reference which will completely get rid of the gravitation the way that we would if the gravitation were uniform. Gravitation is uniform, you go to an accelerated frame of reference falling down with uniform acceleration, and gravity is gone in that frame of reference. No way to do it for the real Earth. The real Earth is a gravitational field which is created by mass, and mass corresponds to divergence of gravitational field. It's the divergence of the gravitational field which gets in the way of trying to replace it by a uniform acceleration. So uniform acceleration is, or how to say it, eliminating gravity by replacing it by a accelerated frame of reference. There's an obstruction, and the obstruction is the masses in the universe create a divergence of the gravitational field. I'm beginning to get tired, so I think I should probably quit any minute now. You need to review some special theory of relativity. Perhaps I'll take another 10 minutes and just remind you of the things we learned about special relativity in previous courses and which I want you to know. Let's see. Yeah.
Question? Inside that elevator, that's where there's special relativity holds exactly.
Yeah.
The Lorentz transformation.
Yeah. We, of course, are studying it in the approximation at the moment of Newtonian physics. Yeah. I don't think I want to do special relativity tonight. I think I won't do that. Instead, I want to talk about geometry a little bit. Geometry and curvature. Curvature is a concept we're going to need, and I think we can just discuss it without discussing physics for a little bit. How do I describe the geometry of this blackboard? The geometry of this blackboard is flat space, just flat two-dimensional space. How do I describe its geometry? The way a mathematician would describe its geometry is by specifying the distance between any pair of neighboring points. If you know the distance between any pair of neighboring points, you can rebuild the entire geometry from that. Knowing the distance between any pair of neighboring points, nearby points, is enough to rebuild the geometry of this blackboard and to discover that it's flat. Let's take a pair of points. Let's characterize them by coordinates x and y, or just let's call them x sub I. I runs from 1 to 2. And here's another point at position x plus dx and y plus dy. 2 points separated by a differential distance dx and dy. What's the distance between them? The distance between them is just dx squared plus dy squared. Well, that's the square of the distance between them. The square of the distance between them, that's called ds squared, is dx squared plus dy squared. That's just Pythagoras' theorem. dx, dy, ds. ds squared is dx squared plus dy squared. Now, that is something which is true if you use for your coordinates nice rectangular Cartesian coordinates. What would happen if I replaced the Cartesian coordinates on the blackboard by some crazy set of coordinates? Coordinates for which the axes were curved in some highly complicated kind of way. There are lots of different coordinate systems that you can use to describe the blackboard. They don't have to all be drawn as a rectangular grid. We could use polar coordinates. Polar coordinates look like this. All kinds of other coordinates. And in general, the lines of constant coordinate, lines of constant x and lines of constant y, would be curves on the blackboard. That would be a general description of the blackboard, not tied to nice rectangular mesh like this. All right, so let's suppose now this could be x equals 1, x equals 2, x equals 3, here's y, and here's x equals 0, here's y equals 1, y equals 2, y equals 3. I have a grid. If I tell you the value of x and y, you can tell me exactly where the point is on the blackboard, but the grid is no longer a rectangular grid. The distance between 2 points is no longer given by dx squared plus dy squared. There's a general formula for any kind of curved coordinates like this, and it looks like this. It's a ds squared, has some coefficients. Whatever it is, it will involve these little differential displacements, and it'll involve them quadratically to the second powers. We're going to go over this again. I want to lay it out for you now. We're going to even prove it. But it's going to be some quadratic form. This is called a quadratic form. dx squared, dx times dy, and dy squared. It'll have all of these things in it. And furthermore, these g's will depend on where you are. There'll be numbers. There'll be numbers, but they'll really be fields. They'll depend on x and y. X, x. I'm really getting tired, so I should probably quit in the next 5 minutes. I don't know how many of you have seen this sort of formula. How many have not seen it? How many have not? All right, so we're going to work it out next time, and I'll show you why this is true. But before I do, let's just go through what some of these things mean. What does it mean to have a G12 here? In the original formula, you had nothing multiplying dx times dy. There's dx squared, there's dy squared. I say more generally, if you think about general sets of coordinates with curvy linear coordinates, then there'll be terms with dx times dy. Do you know what those mean? When there's a term dx dy, it means the coordinate axes are not perpendicular. That's what that means. What about G11 and G22? Those have to do with the relative spread. If we were to make coordinates like this, which were much denser in one direction than the other direction, then the G11 and the G22 would be different than each other. If the coordinates curve and things change from place to place, then these g's depend on position. But the general formula for general curved coordinates for the distance between 2 points looks something like this. And it contains 3 functions of position: G11, G12, and G22. Those functions are called the metric. And we're going to go through, I'm going to show you why that's true. But we're still just describing the blackboard. We're describing the blackboard, and the blackboard could always be described by these coordinates here. When it's true that you can describe a geometry in this simple way like this, the geometry is called flat. Even if you decide to describe it in a more complicated way, if you can find new coordinates that simplify it in this form, it's called flat. This is the hallmark of a flat geometry, Pythagoras' theorem, if you like. There are geometries which are not flat. There are geometries that no matter how you choose the coordinates, you cannot reduce it to this form. Those geometries are called curved. You know an example of curved geometry? The surface of a sphere. The surface of a sphere, you cannot choose coordinates on the surface of the sphere which makes the distance between points dx squared plus dy squared. It's always going to be more complicated than that no matter how you choose the coordinates. What about the surface of a cylinder? Is the surface of a cylinder curved? No, it's not. It's flat. because you can always choose exactly the same coordinates that you would choose if you unrolled it. You can't unroll a sphere and spread it out flat on a surface, but you can spread out a cylinder and make it flat on a surface. Cylinder is flat, a sphere is not. How about, let's see, what other kind of, a saddle surface? A saddle surface shaped like a saddle is also not flat, can't be flattened out. A cone. What about a cone? Yeah, a cone is flat everywhere except at the tip. A cone is flat everywhere except at the tip because you can always take a cone There's a cone, right? There's a cone. At the tip, something's funny is going on, but anywhere else you can unwrap it and spread it out on the table. So you can use coordinates on a cone, except for the tip, which look like this. Cones are not flat, but only at the tip. Cylinders are flat. Planes are flat. Spheres are not flat. How do you tell whether a surface or a given metric like this describes something flat or not? Well, the answer is curvature, which I haven't defined. We're going to define it. The answer is curvature. But curvature is the obstruction to flattening out the coordinates. Tidal forces are the obstruction to getting rid of the gravitational field by changing coordinates to accelerated reference frames. Though that connection is not accidental. Curvature is the obstruction to flattening a surface out or to thinking of it as flat. Tidal forces are the obstruction to removing a gravitational field by coordinate transformation to an accelerated frame of reference. That's the connection we want to build up. The curvature of space and time is essentially the same thing as the effect of a real gravitational field. The real effects of gravitational fields are tidal forces. And that's what we're going to find. The curvature of space-time is the same as tidal forces. Okay, let's quit now before I fall over in exhaustion.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.
Try this.